Hello everyone, this is Dr. Lennon, and we're going to be going over the test 2 review today. So we start off with a chain rule problem. So we have one function kind of plugged into another one. So remember the way we set that up is we say the inner function is what's in parentheses, or typically what you'd do first if you were evaluating some sort of like order of operation type simplification. So our inner function is x cubed, and then our outside function we're going to write as 3 natural log of t. And the point is, if you would replace t with the inside function, you should get the original function, which in this case we do. So the derivative of the inside function, we just do as normal, 3x squared minus 10x. And the derivative of the outside function would be 3 times 1 over t, or 3 over t. And then our derivative here, the way we get that derivative is we do f prime of x, which is we do the in prime times out prime, and we replace t by the original inside function. So we get 3x squared minus 10x times 3 divided by x cubed minus 5x squared. And we can write that as a single fraction if we want. 3 times 3x cubed minus 10x. Sorry, I meant 3x squared. Let me fix that. Divided by x cubed minus 5x squared. And that's it. Again, a lot of times these things won't simplify to in any really direct way, so you just kind of leave them as is. So let's go ahead and move on to the next one. So another chain rule type problem. If you want to write this out without using the kind of calculator syntax, this is really e, and then the entire exponent is x squared plus 1. So here our inside function would be that exponent x squared plus 1. Remember, if you had order of operations, you would simplify in the exponent first. And then our outside would become e to the t power. So inside prime would just be 2x. And for the derivative of e to the t, we just use the regular e to the t rule. So the derivative of e to the t is itself e to the t. So then our derivative, again, we just multiply in prime by out prime and change t back into the original inside, so it becomes e to the x squared plus 1. And that's it. So actually a pretty quick chain rule problem there. So let's go ahead and move on to the next ones, which may involve the product and quotient rule. So for number 3 here, we have a product rule. So again, we can rewrite this if we want as 3x squared minus 5 times e to the minus x. So that's how it's written on the review. It's just kind of translated into the calculator syntax without math print when I copy these over. So remember, we have a product of 2 different functions, a polynomial times an exponential. So we're using the product rule. So the product rule, remember, says the derivative of u times v is u prime v plus uv prime. So we want to pick u to be the first factor, which is 3x squared minus 5, and then v to be the second factor, which is e to the minus x. So u prime here is just the derivative of 3x squared minus 5, which is 6x. And v prime is the derivative of a continuous exponential. So remember, if you're taking the derivative of e to a constant times x, you just multiply in front by the constant, which in this case is the negative sign. And then it's e to the minus x again. So the derivative of e to the kx would be ke to the kx. And then we just copy according to the formula. So f prime of x here is going to be u prime 6x times v e to the minus x. And normally we would write a plus, but we have this negative sign with v prime, so I'm just going to write minus, and then put u in parentheses, 3x squared minus 5 times e to the minus x. And you don't have to factor or multiply out or anything like that. I'm okay with just leaving it like this. So that's fine. So we have one more product or quotient rule before we start looking at some different type of problems. Okay, so I was mistaken. So number 4 is not a product or quotient rule, but we're just trying to sketch a graph that has the following properties. We have a critical point at 4, and the value of the derivative is negative left of 4 and positive right of 4. So basically for our graph, in terms of our properties, that the derivative being negative means the graph is decreasing. So basically we know that f is decreasing until x equals 4, and then afterwards it's going to be increasing because the derivative is positive. So f is increasing after x equals 4. So basically what we want to do is we want to take all of these properties that have to do with first and second derivative and translate them into properties about the function. So an inflection point being positive left of x equals 8 means f, since the second derivative is positive, that means f is concave up before x equals 8, and f is concave down after x equals 8. So there's lots of different possible graphs you can draw. I'll show you just one example. So really we just want to list our two important points here. So we have 4 and we have 8. We don't really care about the y values. We just want to show that we're increasing and decreasing for x equals 4, and then concave up and concave down. So if we're decreasing and then increasing, that means basically this has to be a minimum value, and we have to maintain, so let's say we're decreasing, but we're concave up, so we've got this upward U shape, and then we need to so we need to increase after 4, and still maintain concave up, but then change to concave down, but continue increasing. So notice that this is kind of an inflection point. So what we end up getting is we get a local minimum at x equals 4, and then an inflection point at x equals 8. And that graph will do. So let's go ahead and look at number 5. So let's have a look at number 5 here. So again, if you can't tell, this is x cubed over 3 minus x squared over 2 minus 30x. So for a, we want to find. So we're finding the first derivative here, as I was mentioning before. I had a quick, I had to pause for a second. But anyway, so let's continue. So we have f prime of x. So this comes out to take the derivative of x cubed. You get 3x squared over 3, just leaves us with x squared. Derivative of x squared over 2 is minus x. And then the derivative of minus 30x is minus 30. So we want to find our critical point, so we set that equal to 0, and we go ahead and factor. So we end up with 0 equals x minus 6 times x plus 5. So our two critical points are going to be x equals 6 or x equals minus 5. So we want to create a test value region setup. So we want to put -5 as one of our values, 6 as the other value. So this splits the domain of our function into 3 parts, and we want to test the value of each region in the derivative, so in the x squared minus x minus 30. So as we do that, we need to plug in some number smaller than -5 in region 1. So if you plug -6 into the first derivative, remember we're plugging all of these things into what we found in part A. So if you plug in -6, you end up with a positive value here. You get 42 minus 30, so you'd get 12. So our first derivative is positive in region 1. In region 2, we can just plug in 0. So we'd end up with a first derivative of -30, which is negative. And in region 3, we could plug in some number bigger than 6. So say we want to plug in 7, we'd end up with 12 again. So we end up with a positive value. So basically we can figure out what's happening at x equals -5 and x equals 6 from the first derivative test. So since we change from positive to negative, our function is basically what this means. If the first derivative is negative or is positive, that means our function is increasing. So here, so f is increasing. If it's negative, this tells us that f is decreasing, and then in the last region, f has to be increasing again. So basically what this means is a local max occurs at x equals 5. And if they ask you for the value, we need to plug that into the original function. So and has value, we would say f of 5, and we need to plug that into the original function, the x cubed over 3 minus x squared over 2 minus 30x. So let's figure out what that is. 5 to the third over 3 minus 5 squared over 2 minus 30 times 5. That comes out to negative 725 over 6, I believe, if you plug it into your calculator. And sometimes they'll ask you for the y value, sometimes not. And at the second critical point, we're changing from decreasing to increasing, so we would say a local min occurs there. So this occurs, I wrote x equals positive 5, I meant negative 5. Oh, so did I probably plugged in the wrong number in that case, unfortunately. So yeah, this is incorrect. We want to plug in negative 5, not positive 5. Sorry about that. So f of negative 5, let's plug that in. So we have negative 5 to the third power over 3 minus negative 5 squared over 2 minus 30 times negative 5. So yeah, this comes out to 575 over 6. And the local min occurring at x equals 6 and has value. We want to do the same thing there. We want to plug that back into the original function, f of 6. And let's see what we get. So 6 cubed over 3 minus 6 squared over 2 minus 30 times 6 comes out to minus 126. So that is it for finding the local extrema. Okay, so for number 6, we have an extreme value theorem problem, which means we need to find the critical points, and then from there we need to plug in all endpoints and critical points to find the absolute max and the absolute min. So the derivative here, we're just using, again, the derivative rule for continuous exponential functions. So just bring down the constant and multiply it by the factor. So 2e to the 0.5x would be the same thing, but you'd multiply by the 0.5 in front. So you end up with e to the 0.5x. And then when you take the derivative of e to the minus x, that's just minus e to the minus x. Okay, so to find the critical point, we want to set this equal to 0 and solve. So basically we can add the e to the minus x to the other side. E to the minus x equals e to the 0.5x. And then let's see. I suppose the easiest way is just to equate the exponents then. So we could say minus x equals 0.5 to the x. So, okay, so we could add x to both sides. Clearly the answer is just going to be x equals 0, but I just want to show the steps in case you're a little bit rusty on the algebra there. So we get 1.5 times x equals 0, divide by 1.5. We have 0 equals x as our only critical point. So we need to plug in our two endpoints, negative 1 and 2, and we also need to plug in that critical point we found, 0. So we're plugging these all into the original function, and then the biggest y value is our absolute max, and the smallest y value is our absolute min. So the easiest one to plug in obviously is 0. We're going to get 2, e to the 0 is just 1, so we get 2 plus 1, f of 0 is 3. And then the other ones you may want to use your calculator. So 2 times e to the 0.5 plus e to the negative 1. That comes out to about 3.67. Oh, no, sorry. I forgot the negative 1 when I typed it on the calculator on the first term. So let me fix that. So we get 2e to the negative 0.5 plus e to the positive 1. because we're plugging in -1 for x. So this comes out to 3.93 if you round to 2 decimal places. And then if you plug in 2, you're going to get 2 times e to the 1 plus e to the -2. So 2 e to the first plus, we end up with 5.57. So what does that mean? Well, the largest y value is 5.57, so this is our absolute max. And the smallest y value is 3, so that makes f of 0 our absolute min. So those are our two values. So all set there. Let's go ahead and move on to the next one. So for 7, we're trying to find the inflection points, which is really not so different from finding critical points, but we just need to set the second derivative equal to 0 and set up test value regions for the second derivative. So that's not going to be so bad here. So the first derivative, f prime of x, is going to be 3x squared minus 18x minus 48. And then the second derivative, again, just polynomial, we're just applying the power rule over and over again. We get 6x minus 18. So set f double prime to 0 to find our candidate inflection points and solve. So solving that leaves x equals 3. So the only thing to check is that the concavity does actually change at 3. So we have these two regions. So in region 1, you can plug 0 in. So if you plug 0 into the second derivative here, 6x minus 18, we get minus 18. So our second derivative is negative. If we want, that can say f is concave down. And in region 2, we want to plug in some number bigger than 3 for x into the second derivative, which is going to give us a positive value. If you plug in x equals 4, you get 24 minus 18, which is 6. So that means f is concave up here. So we can say that our function f has an inflection point at x equals 6. So f of x has an inflection point at x equals 6. Okay, so that's it for this problem. Okay, so let's move on to the last few, which are some application problems involving the derivative. Okay, so for 6, we have a word problem where we're trying to determine some dimensions of a rectangular area where we're using basically a long wall for one side of the fence. So kind of we're using a wall on this side, and then we need to fence in 3 sides, and we want to maximize the area of this rectangle that we're using. So let's call the vertical sides y and the horizontal side x. So we know the amount of fence, so we have x plus 2y, that is equal to the 144, and then basically we want to maximize the area, which is just x times y. So if we solve the above equation for x, we get 144 minus 2y. So we can replace x by 144 minus 2y. So we multiply this by y. So let's expand. So multiplying through by y, we get 144y minus 2y squared. Then what we want to do is we just want to take the derivative and find the critical point, and that's going to represent our maximum area. So a prime here is going to be 144 minus 4y. And then we just set that equal to 0 and solve, so we get 144 minus 4y. So add 4y to both sides. We end up with 4y equals 144, divide by 4. So we get our answer, y is equal to 38, I think. So if y is 38, that makes x the other side, 144 minus 2y, which has to be I don't know what I'm talking about here. So not 144 over 4 is 36, not 38. So let me fix that. So we have 36. Okay, so if y is 36, then x has to be 144 minus 2 times 36, which is 72. So basically, in the above picture, so the dimensions that maximize the area are, so let's recall, I think we're using yards in this problem. Yeah, so we're using yards. So we get x equals 72 yards and y equals 36 yards. So typically, if you were going to, so do they ask for the maximum area or not? They say find the lengths of the side. So they just ask for the dimensions. If they asked for what the maximum area is, then you would multiply those two, and 36 times 72 comes out to 2592. But they don't ask for the actual max area, so you're free to stop right there. Okay, so that's it for optimizing the area of this rectangular fenced-in region. Okay, so we have another one of these max-min word problems. So it says we have the sum of 3 non-negative numbers, and that's 36. And one of the numbers is twice as large as one of the others. So let's call our numbers, say, x, y, and 2y. So we know that they add up. If you do x plus y plus 2y, they have to add up to 36. So x plus 3y equals 36. So we're trying to maximize the product of these three numbers, which should be p, let's say, is x times y times 2y. So this is x times 2y squared, and we want to replace that x by 36 minus 3y. So let's replace that. So we have 36 minus 3y times our 2y squared. And if we expand that, we end up with 72y squared minus 6y cubed. So we want to take the derivative of that, set that equal to 0, and solve for y. So p prime would be 2 times 72 is going to be 144y minus 18y squared. So we can set that equal to 0, and we get 144y minus 18y squared. Okay, so this should factor. So if we factor out 18y, we get 8 minus y. So we get either y equals 0 or y equals 8. But we know y equals 0 doesn't make sense as a solution because all of our values have to be positive. So notice in this one it does actually ask for the maximum value of the product. So we know our numbers have to be, so we have y, let's figure out what x is. X is 36 minus 3 times 8, which is going to be 12. So our numbers, we have y equals 8, so also that means 2y is equal to 16. So our max product is, if we multiply those three together, so our maximum product is 8 times 16 times 12. And what does that come out to? It comes out to 1536. So that would be our answer for this problem. The maximum value of the product is 1536. Okay, so on to the last question for the review. So let's look at this last one. It's another optimization style problem, but this one is in the context of cost, revenue, and profit. So we have an ice cream company that at $4 has a demand of 4,000 units, and for every 25-cent decrease in price, we know that demand increases by 200 units. So find the price and quantity sold that maximizes revenue. So the choice for the variable that makes the most sense here is if we let x equal the number of 25-cent decreases. So then our demand, so that's our price. We have two kind of components here if we want to think about it that way. So let me first rather than telling you what demand is. Let's realize that our revenue here is just going to be price times demand. So the price is $4 minus the number of 25-cent decreases. So it's minus 0.25 times x, because x doesn't represent the price decrease, but actually the number of 25-cent decreases, the way that I've written it. So then we have our demand. So what is that going to be? Well, our demand was 4,000 units. And then every time we make a price decrease of x, and we increase by 200. So our demand is 4,000 plus 200x. So this generates our revenue function, which is what we're trying to maximize. So if we call our revenue function r of x, it's 4 minus 0.25x times 4,000 plus 200x. So we can go ahead and FOIL that out to make taking the derivative a bit easier. You could also use the product rule, but I don't think there's any real need for that. So our first is going to be 16,000. Our outside is 800x. Our inside is minus 1,000x. So we're going to get minus 200x in the middle. And at the end, we're getting a quarter of 200, which is going to be 50. So we get minus 50x squared. So you can take the derivative here, which is what we want to set to 0. So we get minus 200 minus 100x. So if we set this equal to 0 and solve, we actually end up with x equals negative 2. So dividing by minus 100, we get negative 2 equals x, which means actually the price they were charging wasn't high enough. They're going to optimize their revenue if rather than, so well, let's just plug those things back in. So our price, optimal price, is going to be 4 minus 0.25 times negative 2. So our optimal price point here in terms of revenue is 450, and our optimal demand, so our demand at that price is, so basically this is plugging in x equals negative 2. We get our demand, which is 4,000 plus 200 times negative 2, which comes out to 3,200. So our revenue is just our price, 450, times our demand, which is 14,400. So optimal revenue under these conditions is 14,400. So that's it. So hopefully that covers your questions on the material that